And just one more really quick example. Let's say calcium carbonate. Calcium carbonate, when you very scientifically heat the snot out of it, you make calcium oxide, and you also make carbon dioxide. So in this case, we're making two new compounds. Again, one of the differences between the compound and our pure substance is I can't chemically break down an element into something simpler. The oxygen atoms, I can't break them down chemically or physically into something else. Calcium carbonate, it's a compound, and I can break it down into new compounds. I can have a compound and I can make elements, the constituent elements from that compound. I'm trying to think if there's something else I want to. Nope, I can't think of anything else. Come back. All right. And I think I used green here. For that other broad general category for composition of a sample of matter. So pure substance, one kind of matter. Constant composition, constant properties. Mixture, they're composed of two or more pure substances within the same physical space. Air is a great example of this. Air, roughly speaking, very roughly speaking, 80% nitrogen, 20% oxygen. Those are not the correct actual percentages, but for this example, it works. The nitrogen and the oxygen are not chemically connected to each other. The pure substances within this physical space retain their own identities. those individual parts are not bonded to each other. They're not bound to each other. Okay, so let's see. Let me go back and fix my spelling here. There we go. Within our mixture, okay, or I should say compared again to the pure substance. There is not a fixed composition. So that is to say that we can have varying amounts of those substances in that mixture. In that mixture, the components retain their own identities. So if I scroll back up here, meaning that all the unique properties of the pure substances remain in that mixture. The properties of a mixture depend on the properties of the pure substances. If I can change the relative amount of both parts of those pure substances, I can have different properties depending upon, again, the relative amounts. I feel like I'm kind of going circular. I'm going to circle back again. So no fixed composition, properties aren't constant. And depend upon the relative amounts of the components. Because we have the properties of the components are kept, right? The identities and components of the components are the same. The properties of the components stay the same. we can utilize differences in properties of the components to separate them out of their mixture. Okay. Now, if I think about what examples I might have where I look at changes in these physical ideas, let me go back to a different color here. Filtration. So that's going to make use of solubility. I'm doing that with my cup of coffee this morning. I really don't like coffee grounds as far as drinking, which means then I need to have some sort of method, some means for keeping those coffee grounds from entering into my beverage. I, of course, use a coffee filter. In refineries, you'll have the various hydrocarbons that have different boiling points. Because the the hydrocarbons are their boiling points can be fairly similar. It's difficult to get a true purification from a very rough separation of boiling points. But what you can do, for example, is separate first sort of very, very light, kind of a medium, what is it? Lightweight, mid heavyweight, and heavyweight. Think about, I don't know, divisions in wrestling or boxing, if you'd like. So you can do that first separation of, I can have my welterweight, and that would be a range of boiling points. And then I can take that mixture, and now it's going to be a finer separation based on their boiling points. Heat the mixture. Lightest. Lowest boiling. Leaves that mixture first. And I do this quite routinely when I want to purify a mixture of two liquids. One of them definitely is going to boil lower than the other one. I set up what's called the distillation apparatus. Boil one away, boil one, and what happens as it's heated, boils, enters the vapor, and we have a tube that's connected to where the gas is that's cold. And so we have the gas, which of course is going to spread throughout the entire container. It hits that cool tube, condenses back to the liquid phase, and then we'll collect that purified liquid. Distilled water, same idea. When we distill water, we tend to be distilling away from dissolved solids. So a little bit different, but same general idea. Same general idea. Okay, so now let's stick with this idea of our mixture. And there's two, again, sort of categories within this realm that we call a mixture. And I'm running out of good colors to use, so we're going to start repeating. All right, so mixture. Go that away, go that away. Homogeneous. Versus heterogeneous. And as you all know, I'm relatively new to Texas, and when I took my foreign language, I went with my family background, which is Germanic and Northern European, and I wanted to learn German because of that. Well, I'm since coming down here, I'm much more interested in learning Spanish. German and Spanish are completely different realms in terms of families of languages. So it's been a slow process. One of the things that I learned early on when studying German, when learning some Korean, when working through the scientific field, which is very much based on Latin and Greek, is to pick up either prefixes or suffixes that keep a unique meaning. The prefix homo in Greek means same. The prefix hetero in Greek means different. When we're talking about a heterogeneous mixture, then something has to be different. Our book likes to talk about this as having two or more phases present. I've got difficulty with that because pizza is composed of solids. Okay, sauce, that's a liquid. Concrete, once it cures, it's made of a solid. gravel. It's all solid. So if we're talking about having different phases, it doesn't work. At least in my mind, it doesn't work. So I'm going to put in sort of the secondary portion to that definition, and that is to say that there are visibly different parts or visibly different compositions within a sample. If we keep that kind of general idea, again, our text likes to talk about homogeneous as being one phase. Okay, fine. Again, I have a slight issue with that because suspensions and colloids are considered homogeneous. Both of those are solids. Well, suspensions are solids hanging within a liquid. The difference is that within homogeneous mixtures, it is the same composition throughout, or the same properties throughout our sample. So we've got uniform properties. The sample. Or again, put a different way, uniform composition. Okay. Your text is one of the first places that I have ever actually observed this distinction. And I think it's fairly unique. They have chemically homogeneous and chemically heterogeneous. Oh my goodness gracious. So let's talk about those pieces right then and there. Okay. For something to be chemically homogeneous, we're talking about pure substances. Only one type of substance. Chemically heterogeneous, then, would be mixtures, where you have two or more types of substances. So that's that's another way of thinking about pure substance versus mixture. Then they put in this idea of physically homogeneous and physically heterogeneous. This is where they're going to talk about things being in different phases or there being a non-uniform distribution. And then, of course, the opposite of that. Oh, I'm sorry. I should have put homogeneous first for both of these. I apologize. One phase or uniform distribution. Let's look at an example where we have something that is chemically homogeneous. And sampling, maybe on your test, we will intend to use different colored or textured spheres, balls, circles to represent different atoms or different elements. So let's keep that idea. This would be an example that is both chemically and physically homogeneous. So I'm going to let my single, I'm going to have little black spheres. And what I'm trying to draw is a relative uniform distribution of those little black spheres through that picture. And let's do this. Let's go ahead and highlight homogeneous with one color, and then we'll use heterogeneous. We'll have a different highlight color. So we'll have, again, we'll stick with chemically homogeneous, but physically heterogeneous. So there's my homogeneous, and let's go sort of a teal color there. Now here, again, I'm going to once again trying to show this as the little black spheres being spread somewhat evenly throughout that little area, and then having that separate box on top, much akin to an ice cube. And liquid. So liquid, water, solid, water. I'm going to recommend that you leave a space in your notes for the other two possibilities. So chemically heterogeneous, and then look at physically homogeneous versus physically heterogeneous, okay? I'm also going to leave to you this notion of the history and names and symbols of the elements. Where do they come from? The abundance, that type of thing. We have what? 9:30, 10:30, 10:50. Okay. We will finish up with a very, very, very short discussion of to finish out chapter 2, unless you are all cool with me just finishing up chapter. Now we'll finish chapter 2 on Wednesday. By way of reminder, a sapling homework. Will be coming out for chapter 1. So it'll be opening up today, probably do a week from Sunday. I may do chapter 2 simultaneous. And we will do a Now You Try It as well. So these will both come open. And what else? Oh, yeah. So look for those to be assigned. Cadre 2, don't forget, you've got a lab report due. And Cadre 1, lab next week. If I want to, then I could put in date. Cadre 2 off on Monday. Just to finish up. Any questions?
No, ma'am.
Okay. Nothing at all? I'm fine with no questions. Totally fine with no questions. Okay, well, you all, thank you so much for coming. I enjoy, even if it is sort of black boxes on the bottom of my screen. I very much enjoy having people with me. And again, if you have any questions, please, please, please feel free to speak up. Otherwise, have a fantastic weekend.
Yes, ma'am.
Bryce, I do have a question.
Yeah, go for it.
So earlier we were looking at a few different chemicals and like their numbers and letters and names and symbols. Are we going to be looking further into that later? Are we going to need to know how to combine them or split them up?
Yes and yes.
Okay.
Yes and no. Sorry, Caleb, not the best answer for you. I realize. You will always have access to a periodic table.
Okay.
And my plan is not necessarily to make you memorize anything off the periodic table. My goal is to have you learn how to use that as a tool.
Okay.
And as far as memorizing names and symbols, I will put a list out of names and symbols that you're going to, again, it goes back to a vocabulary idea, Caleb. It's not necessarily I'm going to make you memorize that hydrogen is H, carbon is C, and so on. But if I start just rattling off names and writing down their symbols, it's going to be useful for you to have that vocabulary. And as far as putting compounds together, that is something that we will be doing. And again, familiarity with the elements, the symbols, is going to be very helpful. So